Okay, so let's continue with chapter 3 about image processing. For the students that are watching this lecture online, can you tell me if you can listen to me? Okay. So let's begin by first reviewing the topics that I have covered in the previous lecture, which corresponds to point operators, linear filtering, and other neighborhood operators. In point operators, we have seen that we can apply simple intensity transformation functions to modify the appearance of the object in the image. And in linear filtering, I have explained how convolution and correlation work. And there was an issue with when we applied linear filtering, and it was that after we apply these filters, there are some blurring effects or blurring artifacts. And I pointed out that if we use nonlinear filters, uh, we can decrease the effect of these blurring artifacts. So now I'm going to move into section 3, corresponding to more neighborhood operators. So in this section, I'm going to introduce the edge-preserving capability of nonlinear filters, including bilateral filtering, and also operations over binary images, which regard neighborhoods as well, and to change the shape of objects within with a binary image. Okay, before addressing image denoising, we can think about image noise as random intensity variations, which degrades the quality of an image. And for instance, in this figure, we can see that the presence of noise in the image. On the left, we can see the presence of salt and pepper noise. And on the right, we can see the presence of Gaussian noise. And if we apply linear filtering to the image with salt and pepper noise, we can see that the edges in the resulting image looks very blurry. But if we, the same, if we apply linear filtering to an image with Gaussian noise, still the results are not the best because we cannot recognize the edges on the resulting image. So instead of combining all the pixels within the neighborhood, we can simply take the median value. To do so, we can take the entries of a neighborhood, like this one. This is the neighborhood. So we take the entries of this neighborhood and take the mean value, which in this case is 4, and then replace that value to the original pixel, which it was 97. And it is very evident that even though the noise has been, sorry, okay. So in this example, we can see how the high frequency salt and pepper noise is basically removed after applying the medium filter. For instance, this is the image with salt and pepper noise, and after we applied the medium filter, we can see that basically all the noise has been removed. But this is not the case when we have Gaussian noise. After we apply medium filtering, we cannot still determine the edges within the image. So that means that even though medium filter preserves the edges, or in some cases it preserves the edges, is not the best option for all the cases. Okay, so another approach is to average certain values of pixels neighborhood. This is the case of applying alpha trim average. The working principle is very straightforward. Similar to the median, we sort the values of the neighborhood. The same as this one. We sort the values of this neighborhood, and we removed elements of this neighborhood according to the alpha fraction. For instance, in this example, the value of alpha is 0.25, which means that we have to remove the lowest values and the highest values as well. And after removing those entries, we computed the mean or the average of the remaining values. But there is an interesting property when we use alpha trim mean, and it is that if we set the value of alpha to 0.5, we're basically applying the median filter. And if we set the alpha to 0, it's basically a mean filter or a box filter. And if we take a value in between, it's a hybrid between the mean and median filtering. Okay. So the previous two nonlinear filters regard the intensity of a pixel's neighborhood, even though a neighbor is distance for the pixel. So a better approach is to regard the distance between the neighboring pixels and the pixel we want to modify. Actually, this is how bilateral filter works. According to the definition, we have a weighting function or kernel denoted as W. Sorry. This is a weighting function or the kernel. But this kernel regards the distance between a neighbor and the pixel we want to modify. And it also regards the difference in intensity between the neighbors, and also the difference in intensity between the pixel and the neighbors of that pixel. And finally, the weight function or the kernel of this bilateral filter is just a product of the domain kernel, which regards the spatial information or the distance between pixels, and the range kernel, which regards information about the difference in intensity. At the end, we simply multiply these two kernels to obtain the bilateral filter kernel. So the domain kernel regards spatial information, which represents the distance between the pixel we want to modify, and the neighbors of that pixel. And in this case, the kernel is shaped as a Gaussian function. We use the same approach for the range kernel, but for the range kernel, we employ the distance of the pixel we want to modify and the neighbors of this pixel. And it is important to notice that the domain kernel is the same for every pair, for every pixel in the image, but the range kernel it depends on the pixels and also on the neighborhood of that pixel. Okay, in this simple example, we can see how the domain kernel and range kernel operate. As I said, the domain kernel is the same for every pixel, and we can see that the weights decrease with the distance. For instance, this is the pixel we want to modify. Okay, so the distance between the pixel and itself is 0, so the weight is just 1. And as we move farther from the pixel we want to modify, the weight of the domain filter or the domain kernel decreases. But this is different from the range kernel. For instance, the neighbors whose intensities differ too much from the pixel we want to modify, in this case 7. For instance, if we take this pixel 1, we can see that the value for the kernel is close to 0. But if we regard a pixel whose intensity is close to the pixel we want to modify, this one, it reaches a highest value in the kernel, in the range kernel. And after that, we just multiply the domain kernel with the range kernel. Okay, this is a more intuitive way of seeing how bilateral kernel is applied. In this image, we can see a 3D representation of a noisy edge, and we want to compute the bilateral kernel for this pixel. This is the pixel we want to modify. So the pixel is located in this part of the image, and we have a Gaussian-like domain kernel, which is this one, and also the range kernel, which is on the right part of the image. And after we compute the range kernel and the domain kernel, as I said, we just multiply both kernels to obtain the final bilateral filter or bilateral kernel, and apply this kernel to modify the pixel in the middle. And the result of applying a bilateral filter into the whole edge or to the whole image is this one. And as we can see, the noise has been removed, but we can still see the edge, or we can still see the step on the resulting image. That's why I said that using bilateral filtering, we can preserve the edges on the image.
Presenting the topic now is chapter 3, pololinear. Yeah, so Lin Baoluo, and he's my PhD student, and I hope he can get the highest mark. Yeah, 10,000. Yeah, try your best. All right.
So to have a better picture of how bilateral filtering reduces blurring at the edges, we can take a look at this example. This is the original image. On the left part of the image, this one. And noise is applied to this image to obtain this image. And we apply filters. First, linear filtering to obtain this one, and also bilateral filtering to obtain this image. And as we can see in the resulting images, there are more blurring artifacts when we use linear filtering. We cannot easily spot the edges on this image. But if we apply bilateral filtering, we can remove or we can reduce the noise, but we can still preserve the edges of the image. However, it is worth mentioning that different from the other filters, bilateral filtering is more computationally expensive because we have to compute a range kernel for each pixel, which is this one. We have to compute this kernel for each pixel, which is more computationally expensive. So besides filtering, we can employ neighborhood operators to change the shape of a binary image. A binary image does not contain any intensity information, but labels are assigned to each pixel according to its meaning within the image. For instance, if we want to represent the region containing a face, ones can be assigned to the pixels depicting the face, while the background or other objects are labeled as zeros. The simplest operation to obtain this kind of binary images is to apply thresholding, which means that pixels above a threshold are labeled as 1, and pixels below the threshold are labeled as 0. So this is the simplest operation to obtain a binary image. And also, after an image is binarized, we obtain several regions, and the shape of these regions can be modified by applying morphological operations. This is a very simple Okay, so we refer to these regions as binary objects, and the goal is to change the shapes of these objects according to a neighborhood operator. Now, these morphological operations can be defined as binary convolutions according to the textbook, followed by thresholding operations. And the most common operations are dilation, erosion, opening, and closing. And to apply morphological operations, we first threshold the image C, which is the result of a binary convolution, and then we apply different thresholding values. For instance, for dilation, we apply a thresholding of 1. For erosion, we apply a thresholding of S. S corresponds to the size of the kernel. Opening is a combination of dilation and erosion, and closing is also a combination of both operations.
我点评一下那个林子柔，再说林子柔，那个汉阳，请你打电话给林子柔，你有没有他的那个手机？我先把它送给你啊。对啊，keep going.
Okay, so this is a very simple example of applying dilation, erosion, opening, and closing. We have a binary image, I, and a kernel. This is the binary image, the original one, and the kernel, this one. And if we count the number of 1 entries, or entries having a value of 1 in the kernel is 5. So we have 5 1 entries in the kernel. And after we apply binary convolution, we obtain this image. And just to have an idea of what is the meaning of this binary convolution, it's just we count how many entries of label 1 in the kernel match with the entries, the 1 entries or entries labeled as 1 on the image. For instance, if we take this pixel and we apply binary convolution, we just have to count how many pixels or how many neighbors around these pixels, this pixel match with the binary kernel, which in this case is 5. So it's very straightforward to compute the result of a binary convolution. And to compute the morphological operations, we threshold the convolved image. For instance, for dilation, we apply a threshold of 1. So all the entries in the original, on the original image resulting from the convolution, all the entries having values below 1 will be removed or will be labeled as zeros. As we can see, for instance, we have these entries, this one. So all of these entries have value below 1, so we remove from the binary image, and all the entries having a value larger than 1 are labeled as 1 in the new binary image after dilation. So we can see that after dilation, we are thickening the objects in the binary image. This is the opposite when we apply erosion, because we use threshold of S, which is the number of entries with a label of 1. So for instance, we only have 2 pixels within the image that are larger or equal to 5, which is the number of entries with label of 1 in the kernel. So accordingly, we just keep these 2 pixels for the resulting image, the resulting binary image, and all the other pixels or the remaining pixels are labeled as 0. And the latest 2 examples are combination of dilation and erosion, which correspond to opening and closing. And opening correspond to first applying dilation and then, first applying erosion and then applying dilation. And closing is the opposite. We first apply dilation and then erosion. So in both cases, for opening and closing, we first apply a convolution, a binary convolution, then a thresholding operation. And for the remaining operation, we have to compute, or we have to apply convolution again and threshold. So we basically apply convolution and thresholding twice for opening and closing. Okay, so another operation over binary images is the generation of distance maps, which comprises the computation of the distance between a pixel with a label of 1 to any 0 entry on the binary image. And in this example, the CD block is employed to compute these distance maps. So we can see that in the resulting value is the minimum distance between any 0 entry in the horizontal or vertical orientation. For example, for this pixel, we can see that the distance between that pixel and any pixel labeled as 0 is 2, according to the CD block distance. And one application of these distance maps is that we can improve the construction of panoramas. Panoramas is an image processing operation where we want to blend images of the same scene, but taken from different perspectives. We want to generate a bigger picture from these images. But you're going to learn about this panorama generation in section 8. But to improve the generation of these panoramas, this technique of using distance transforms is very common. And after binarizing an image, it depicts several regions, as we can see in this example. We can see a binary image, and there are several regions or isolated regions. And after we obtain this binary image, we want to analyze each region independently. And to do that, we have to find the connected components within the original binary image. For instance, in this example, we have 6 connected components. So we want to analyze each connected component independently. And after obtaining these connected components, their morphological properties can be further analyzed. For instance, we can compute the area, which is just the number of pixels comprising the connected component. We can compute the perimeter, which is the number of boundary pixels or pixels that are in the boundary of this connected component. We can get an approximate location of of the connected component by computing the centroid, or we can get more insightful properties from these connected components by using the second moments. Okay, we can determine the main axis length and also the orientation. For instance, we take a look at this connected component in green, we can see that the orientation of the main axis is close to 45 degrees. So we can get these properties of connected components by using the second moments of the regions within the binary image. Okay, so
yeah, so it's more important. Yeah.
I like that guy. What's your name? Suck dick?
It's money.
Appreciate the offer.
Oh, yeah.
Thanks so much for coming tonight. I'm sure you're very busy all day. I'm going to talk to you for the rest of the show. You're in a relationship? What's his name? Oh, you're straight. Just sucked it. I get it. My brother, I love you, man. From the bottom of my heart, you have a great sense of humor. But please, change your name. There's a beautiful Indian name that I can help you with. It's one of my favorite Indian names. Good pussy. Much better name. Good pussy. Good pussy. Much better than something. Only because you're straight. Now, if you weren't straight, that would have been a perfect name. Wow, you would be the luckiest gay guy ever put a front page. Okay, no problem. What do you do for a living? I accept it. No, stop now. I would never stop. Stop. I'm gonna stop. Because I mean, I love how you're laughing, so you're amazing. What's your job? What do you do? Europe? SAP? That is? He has IT? But you're also Indian? She translated for me. Max said, we knew you were stupid. Everybody knows what that is. I tell you the abbreviation stands for IT. Thank you, I appreciate it. Do you know something? He's the nicest guy in the world. In Australia, when you say your name, do people like joke with you? Nobody. They get scared. They're like, oh shit. Not right. Keep going back. Alright, stop here, okay? Can I be honest? You have superpower with the name something, you know? If you're gonna live in a society, English-speaking country, and you're like, no, I'm not going to change my name. I am something. It's a beautiful Indian name. You don't like it? Suck my dick. I swear to God, Indians, not only the nicest people, but they have the best sense of humor in the motherfucking world. And you're the prime example of it. What a dude, man. 10 minutes to talk about his name, but he didn't give a shit.
Okay. And the previous operations we have studied modifies an image in its original domain or the spatial domain, but some filtering operations can be better understood if we take a look at the image in the frequency domain. To do so, we have to use Fourier transform. It's the most common tools for analyzing an image in the frequency domain. Okay, so in this section, I'm going to present the definition of these transforms. How can we leverage these transforms for frequency domain analysis? And besides analyzing the image operation in the frequency domain, we can use these transforms for data compression as well. So according to Fourier analysis, any signal can be represented as a series of weighted sines and cosines. And we can regard the concept of frequency as the presence or of smooth or sharp intensity variations. If the change in intensity is smooth, we can regard this as a low frequency component. And if the change is sharp, it depicts high frequency. Okay. So we can use transforms or Fourier transforms to analyze the effect that a filter in the spatial domain has over different frequency components. And we can also filter an image in the frequency domain and obtain the results of this operation. We can use also Fourier transform or a variant of Fourier transform for image compression. In this case, this is a very common algorithm in JPEG where they apply a blockwise transform, or they perform these Fourier transform operations over different blocks in the image, and then apply quantization to reduce the size of the image. And it is important to notice that if we modify an image in the frequency domain, we can see its effect in the spatial domain because the Fourier transform is reversible without information loss. So we can go from the frequency domain or apply the Fourier transform, modify the image, and go back to the spatial domain. We can have a better understanding of the analysis in the frequency domain by taking a look at these examples. The frequency spectrum on the bottom, these are the frequency spectrums. Okay, so the frequency spectrum represents the magnitude of the frequency components, or the pixels close to the origin represents low frequencies or low frequency components. So this is the origin. This is the origin, and all the components that are close to the origin are regarded as low frequency components. And as we move far from the origin, we can see high frequency components. For instance, if we analyze this part of the spectrum, we are analyzing a high frequency component. And for instance, on the left, we have an image with very smooth transitions. So we can see that the spectrum is concentrated on the origin. There's only high magnitude in this part of the frequency spectrum, which is a horizontal line, because even though the transitions are smooth, there are still some changes or some edges within the original image. And if we take a look at the example in the middle, we can see an image with evident blur. So if we take a look at the spectrum, we can see that most of the components are concentrated at the origin, and only there are some low magnitude components or low magnitude high frequency components. For instance, in this part, we can see that the magnitude is very low compared to the origin. And in the example on the right, we can see the presence of high frequency components because there are many sudden changes or sharp changes in intensity. So basically, the whole spectrum is the frequency is the components are spread all over the spectrum. It's not longer concentrated in a single point, but it covers the whole spectrum. So in this case, we can say that the image presents low frequency components, middle frequency components, and also high frequency components. Okay, as I mentioned at the beginning of this section, we can employ Fourier transform to see the effect of a filter in the spatial domain. And in this figure, there is a single sine function. This is the input to the filter, a sine function. And after filtering the image, we can see that the amplitude or the magnitude of this sine function has been modified, as well as the phase of the sine function. Which means that after applying a filter, the amplitude of the signal is modified, as well as its phase, according to the frequency of the input signal. And by using Fourier transform, we can compute the value of the resulting amplitude and also the change in phase for multiple frequency components. And this is the definition of Fourier transform. This is the original image, the original signal, H, and this part in blue is the kernel of the transformation. And as we can see, the kernel is complex valued. So that means that after we apply Fourier transform, the result is a complex valued function. Two-dimensional signals or images, as we can see in this definition. And besides using Fourier transform for frequency analysis and filtering, we can use its variant called discrete cosine transform to perform image compression. And different from the original Fourier transform, discrete cosine transform is real valued. There is no complex value kernel. In this case, the kernel is just a cosine function. This part in blue, and the original signal or the original image is Fi. Okay. And we can extend this definition to images to obtain the two-dimensional discrete cosine transform of an image. And we can employ this transform to perform data compression. This is a very simple pipeline of how can we perform image compression. First, given that the discrete cosine transform is real valued, we can apply the discrete cosine transform and remove some high frequency components to obtain this variant of the discrete cosine transform. And then we apply quantization to the transform, the discrete cosine transform. So this is after we apply quantization, we are reducing the size of the we're applying compression to the image after we apply quantization. So this result is actually a compression of the original image. And to obtain or to recover the image that we have compressed, first we apply dequantization to obtain a discrete cosine transform of this new image, and then we apply the inverse of discrete cosine transform to get a recovered image in the spatial domain. This is a very simple pipeline, but it's very similar to how JPEG works. Okay, let's take a 10 minutes break.
Mhm.
Okay, so the interpolation kernel is defined as H in this part of the figure, and the original discrete signal is Fk, denoted here. And the resulting signal is a continuous signal denoted as G of I. And now we have to define how we're going to mix neighboring pixels or neighboring points to define this continuous signal. And in this example, I'm using a 10th interpolation kernel. And for instance, we want to know the value at this point. We want to know the value of this point, and for that we use these 2 points, this part of the figure and the other one, this part of the figure, and we want to know how can we mix or how can we use these two points to obtain this value, which is not defined in the original signal. And if we use the kernel, for instance, the kernel defined at this point, we combine the value of the kernel at this point in the continuous domain and the value of the kernel from this point. We can see the kernel is like a triangle in the image. And we end up with these two values in black. So we just aggregate, or we just sum these two values to compute the interpolated value. So this is very similar to convolution, but in this case we're dealing with a discrete signal, and the kernel is a continuous one. So that's the difference between applying regular convolution in discrete signals and applying interpolation. And after performing interpolation, we end up with a continuous signal, which we can see in red in this part of the figure. We can see the signal in red, the continuous version of the signal. And after we have this continuous signal, we can resample the signal to increase the number of samples. In this case, we have the original signal, or the original discrete signal has a sampling rate of R sub S, and we have a target sampling rate, which is R sub T. And for this specific application, the sampling rate of the source signal is lower than the sampling rate of the target signal. And the opposite is signal decimation. In this operation, we want to decrease the number of samples. So in interpolation, the goal was to reconstruct a continuous version of the discrete signal to increase the number of samples. But in this case, we want the opposite. We start with a discrete signal with more samples, and we have to figure out how to decrease the number of samples of this signal. But to accomplish this, first we have to convolve the original signal with a low-pass filter, because as you have seen in section 2, there is a aliasing effect if we just apply downsampling without low-pass filtering. So now going to detail how we construct an image pyramid. Pyramids are very useful when we want to find certain features like edges or more complex structures, but the problem is that these structures, these edges, or other more complex features, we don't know the scale at which these structures appear in the image. So we have to perform the same operation to images, but at different scales. And to construct this multi-resolution representation, we required to perform upsampling or interpolation and also downsampling for reducing the size of the original image. For instance, this is the conventional way of constructing a pyramid where the original image is located at level 0, and for the levels above the level 0, the image is downsampled by a factor of 2. And in the image on the right, this one, in this image, I want to find the left side of the subject's jaw, which is this. I want to find this part of the subject. And to do so, I'm employing 11 by 11 hard filter, which is very common. This filter is very common in facial detection. And I apply the same kernel, but with images at different scales. So if I apply the kernel to the image at level 0, I cannot spot very easily what is the jaw of the subject. If I downsample the image and perform the same operation at level 1, the results are better. But still, it's not very easy to spot the jaw of the subject. And finally, I perform the same operation at level 2, and now we can easily spot the subject's jaw in this resulting image, which is this part. When I said that it is not easily to spot what we are looking for in the image is that the response is not very high, or it's not very visible on the resulting image. In the original, when I applied this filter to the image in level 0, we can still see information that is not relevant to find the jaw of the subject. And the same for level 1, we can still see information that is irrelevant. But in level 2, we finally find in a very easy way how to spot this body part that we're looking for in the image. Another way of representing an image in multiple resolutions is by using wavelets instead of pyramids. This is a conventional or the most common pipeline for using wavelets for decomposing an image at multiple resolutions. For instance, we start with an original image here, and we apply high filtering or high frequency filtering and low frequency filtering, and we downsample the image, both the high frequency and the low frequency, and obtain 4 blocks, which correspond to this block, this block, and this block. So we have 3 high frequency representations at level 0, and we can continue with the decomposition for further levels or for different scales. For instance, the resulting image in this part of the composition is further decomposed into level 1. Okay. And after performing the composition, we can reconstruct the image at different levels or at different scales. And to do so, first we apply quantization to the high frequency levels. For instance, we are at level 0, so we have three high frequency maps. The original high frequency maps were quantized, and the low frequency or the low frequency representation in the wavelet is actually reconstructed from level 1, which is this is the composition of level 1. Okay, so we are obtaining the low frequency representation at level 0 from the level 1, or the representation at level 1. And we continue with the reconstruction until we have the whole image at the end. Okay, so this is a very simple way of performing wavelet decomposition and wavelet reconstruction. And besides representing the images at different scales or different resolutions, we have to keep in mind that there is a difference between using wavelets and using pyramids. And wavelets are filters that localize a signal in both space and frequency. In this part, or in the pipeline of wavelet decomposition, we have high frequency filters and low frequency filters. And these filters are actually wavelet filters. So these are a special family of filters that we use for performing wavelet decomposition. And wavelets provide a smooth way of decomposing a signal into frequency components without blocking, and are closely related to pyramids. When I said without blocking, I mean that after we perform reconstruction, there are no blocking artifacts in the resulting image. That is a property of wavelet reconstruction. And also that traditional pyramids are overcomplete, which means that for representing an image at multiple resolution, we use more pixels than the original image. But if we use wavelets, we basically keep the same number of pixels to represent the image at multiple resolutions. For example, we can see in this decomposition that each time we perform the composition at different levels, we're reducing the size of the low level image, which is this one. But if we consider the size of this decomposition, it is actually the same size as the original image. Which means that if the original image is h times w, the composition map is also going to be h times w. So we can see that performing wavelet decomposition actually keeps the original size of the image. But if we perform pyramids, we require more pixels than the original one.
How long have you been single? 3 months? You gotta meet a really nice guy tonight. This guy, how are you? What do you do? Oral surgeons. Nice. Take it easy. I'm thinking for you. Trust the professional. She is dead gorgeous. Don't this up at me. How long have you been single? You're a good-looking guy. You're a oral surgeon. 5 years you couldn't meet anybody to be in a relationship? Why? COVID. Okay, he's such a nice guy. Because of COVID, 5 years he couldn't make out with anybody. You friends with this guy? Where did you meet the guy? I mean, residency together because you're all oral surgeons? Was he a nice guy? He was on time. He was professional. Does he know how to orally? He's an oral surgeon. Is he good orally? Yes? You practice all the time. 5 years you've been practicing? So how does everything go? Have a dummy or something? You just... Good for you. I really like you. Where are you going to take your first date? Take her somewhere really nice. I'll pay for the date. Okay? First date is on me. Yeah, absolutely. Yes. I will pay. And then the following week, I'll come here for oral surgery. Who's that guy? Yes. Come here. Sir. Hi. What are you, every time I look at this guy, these guys are just... He's sleeping. It's never happened ever at my shows. This guy came here to destroy my self-confidence. Because he's a comedian, I'm going to live sleeping in the show. Who the fuck are you? He's sitting from a whole other seat. You like me now? You know this guy? Why are you not sitting next to him? You're scared of him? So, hey, are you on drugs? Did you smoke something? So, I couldn't get the work of any drugs today. Maybe that's the problem. We had a lot of things to do. Yeah, but you didn't fucking understand everything what happened. You slept the whole show. That's your wife? Oh, what a nice lady. Oh, that's sweet. So what happened today? I promise you, you don't know what I've been going through today. They closed my surgery because I had a water leakage in my whole surgery. So I had to go. Wow, they closed the surgery because you had leak? Leaking water? The what? I didn't say you leaking. Because I'm not leaking water. Never mind. You're a surgeon? You're a doctor? You're a dentist? You're not a doctor, you're a dentist. You know him? That lady is screaming. You have a problem with your tooth right now? You're hurting? I hear you crying. I know the surgery is closed. I'm sorry to break the news. He's leaking water. I'm sorry, he's not leaking water. One of his pipes leaking water right now. But maybe he's not here. He probably will do the surgery in his kitchen. Yeah? He said, I agree. Yes. You will do this. Okay, come tonight. Yeah? See, I got you a customer. You're awesome, Sven. I'm sorry the water's leaking, you know? I feel now bad I woke you up. You know, I'm sure, listen, I'm going to come to your work today. We're going to fix the pipe. It'll be an honor for you for me to change the pipe. So now it's your pipe.
Okay, so now I'm going to move into the last section of this lecture, which is about geometric transformations. In the beginning of this chapter, I defined the difference between intensity transformation and geometric transformation, which means that in intensity we are actually modifying the range of the image or the intensity. And in geometric transformations, we're modifying the domain of the image or the pixel positions. So first, I'm going to detail some parametric transformations. These are very basic geometric transformations like scaling, rotating, perspective transformations, some warping algorithms. In the textbook, they are included in the textbook. There are two warping algorithms, and also how image warping is framed as a resampling problem. And finally, the last section is mesh-based warping. So in parametric transformations, it's a geometric transformation that apply a global deformation to the whole image. Or in other words, the deformation is controlled by a small number of parameters. Just to remind you that this is the definition of a geometric operation, where the operator is h, and it is modifying the domain of the image. And these are the most common geometric transformations, or the most common global transformations. For instance, we have translation, which preserves the orientation of the image, but just move the image to another part, or just move the pixels from one part of the image to another without rotating or scaling. Uh, the rigid transformation, which comprises rotation and translation, again, it preserves the length of the original image, but in this case, the orientation is changed because we're applying rotation to the original image. Similarity, which is a mixture of scaling, rotation, and translation. In this case, only the angles of the original image are preserved, because we're scaling the image, which means that we can make the image larger or smaller according to the scale. We can rotate the image, or we can move it to a specific location. And the affine transformation preserves the parallelism of edges or lines in the original image. This we can see of this affine transformation as a general form of performing rotation translation. So we can perform rotation translation as an affine transformation. And the last one is projective, which only preserves the straight lines. We can see of this projective transformation as taking an image in an original plane and try to project the objects in this original plane to another plane. This is very common in stereo imaging, or taking two images to estimate the distance between the camera and the object. So there are two image warping algorithms. The first one is forward warping. The second one is inverse warping. And for forward warping, we start with the original image, and the location of the pixel we want to modify is an integer, and we apply, for instance, a rotation. And now the location of the pixel in the new image can be an integer, or can be a real number, or a float number. That's the problem with forward warping. And in the other case, in inverse warping, we start with a position in the target image, which means that the position in the target image is an integer, and we apply the inverse of the rotation to find which pixel should be taken to the new target image, or which pixel should be processed to compute the intensity of the target image, of the target pixel. So in this case, the problem is different. In forward warping, we start with an integer position, and probably the target position can be a float number or could be non-integer. And in inverse warping, we have the opposite. We have an integer position in the target image, and the position in the original image might be non-integer. So in this case, for inverse warping, we reframe the problem as a resampling operation, because uh, similarly as in interpolation, we want to know how can we determine the intensity of this position, which is non-integer. That means that we have to reconstruct, or we have to find how can we compute the intensity at this non-integer position. So that's how we can frame the inverse warping as a resampling problem. Okay, so in this transformation, the deformation, as I said, is controlled by just a small number of parameters and is applied in the same way to all the pixels in the image. For instance, for translation, we only have three parameters. Sorry, two parameters. For the rigid, which comprises rotation and translation, we have three parameters. Similarity, we have four parameters. For affine, we have six. Projective, we have 8 parameters. But sometimes we need to perform warping. Uh, we have to perform a different warping operation to different parts of the image, and this is called mesh-based warping. For this case, the transformation or the deformation is not defined by a small number of parameters, but in this case, for instance, in mesh-based warping, we divide the image into a grid, and we move the points comprising the grid to apply geometric transformation. For instance, we have an example here. We start with an original image. We find the grid points on this image, and we shift the points comprising the grid. And after we shift the points in the grid, we're basically performing a geometric transformation, or we're warping the original image. In this case, this example corresponds to free-form deformation, which is a very common technique in CAD, in CAD. And for this transformation, there are deformation fields, which define how we're going to move one pixel to another location, or how we're going to shift the intensity of that pixel to another position within the image. That is defined according to deformation fields. Okay, so these are the two types of geometric transformations that are included in the textbook. Okay, so this is the end of the lecture. Let's take a 10 minutes break. Okay, in this presentation, I'm going to introduce the research I've been conducting at the Digital Camera and Computer Vision Lab. My research is mostly oriented toward lightweight models. In this case, the title of my research is Lightweight ResNet-based log for low-rank visual representation learning. And first, I'm going to introduce some concepts about foundation models and visual representation learning. Basically, foundation models and visual representation learning turn around architectures, training regimes, and downstream tasks. For architectures, we have foundation models, which are huge models that are pre-trained on very large data sets. And of course, the accuracy or the performance is state of the art or is the highest. And we also have lightweight models, which are meant to have an accuracy or a performance close to foundation models, but without a large number of parameters. And also, we can run these lightweight models in very in constrained devices like a regular computer or an edge device. And about training regimes, usually for foundation models, there are two stages. First, pre-training and then fine-tuning. And during pre-training, the foundation model is trained on a data set, for instance, ImageNet for classification, image classification. But after training the model, we can still use part of the model to another task like pose estimation, image classification, semantic segmentation. And the way to adapt this model for other downstream tasks is by applying linear probing or fine-tuning or parameter efficient fine-tuning. And there are some problems when we develop foundation models. The first one is that very large models, especially for visual representation, suffer from exploding gradients, which makes optimization and training stability difficult. Also, self-supervised pre-training, which aims to learn representations without any labels. For this, some pretest tasks can be used for self-supervised pre-training, like contrastive learning, masked image modeling, or image reconstruction. And as I said, supervised pre-training is one of the most common way of training a foundation model. The most used data sets are ImageNet 1K and ImageNet 21K. And this during this supervised pre-training, we give the foundation models strong initialization for downstream tasks. So in large vision models, the vision transformers were introduced in the 2020s. But initially, or the early versions of these vision transformers performed worse than previous developed convolutional backbones for dense prediction tasks like object segmentation and object detection. So to address this limitation, the researchers proposed to combine convolutional neural network with vision transformer to improve the performance of the pure vision transforming models. So the first strategy to to mix convolutional neural networks with vision transformer is to replace the fully connected layers with convolutions. And the second strategy is to partially integrate convolution using a token feature reshaping while preserving the core vision transformer structure. And regarding lightweight models, there are plenty of techniques to reduce the number of parameters when training a model. The first one is stepwise separable convolution, which is a very common technique when we are developing convolutional-based backbones. The second one is bottleneck modules and knowledge distillation from bigger models to smaller models. And the last one is model compression. Of course, there are more techniques, but these are the ones that are mostly used in the works I have reviewed. The first one is very simple. It performs stepwise separable convolution, which replaces full 3x3 convolution in ResNet blocks by using a 3x3 stepwise convolution followed by 1x1 convolution. So this reduces the number of parameters. This reduces the number of parameters required to perform convolution within ResNet architecture. The second one is bottleneck models. For instance, this is the bottleneck that is used in ResNet-based backbones. And also we can introduce bottlenecks blocks into transformer-based backbones, like in this work, which is bottleneck network for transformers. And also we can use knowledge distillation, which aims to introduce features or introduce representations within obtained with a larger model to a smaller model. There are three approaches to perform knowledge distillation. The first one is feature-based, which aims to minimize the difference between the features obtained with a teacher model and the features obtained with a student model. The second approach is similarity-based, which just considers pairwise similarities between features or instances. In this case, we don't want to minimize the differences. We just want to compare similarities, which could be any kind of similarity measure. And the last one is logic-based knowledge distillation, which aims to reduce the difference between the last part of the two models, between the teacher model and the student model. So these are the three approaches to perform knowledge distillation, and the way it is applied from to obtain lightweight models with knowledge distillation is to use the teacher, which is order of magnitude bigger than the student, and use it to guide the training of the student model. So the first work I found related to combining convolutional neural networks with vision transformer is this pyramid vision transformer. But there are some limitations in the first version, which is that non-overlapping patches break local spatial continuity, and also it's very expensive for high-resolution images. And in version 2 of this pyramid vision transformer, they introduced this hybrid convolutional neural network with transformer design. So in this case, I want to point out that the first version of pyramid vision transformer was full transformer-based, was a full transformer-based backbone. But in the second version, they introduced this mixture, this hybrid design. And these two backbones are pre-trained on ImageNet for image classification. And of course, this is a supervised pre-training. As I said, this is the most common type of pre-training for these uh, foundation models. The second one is Swing Transformer. In this case, I'm focusing on the second version of Swing Transformer. And again, they mm, mix the convolutional neural network architecture with a transformer based architecture to address activation instability when scaling vision transformer. This is the instability that happens in Swing Transformer as the model is scaled up or as we increase the number of parameters. In this curve in red, we can see that the activation starts to increase to the point that the training is no longer stable. But by introducing the techniques, the new techniques into the second version of Swing Transformer, they reduce this instability, and now the number of parameters can be increased without having this exploding gradient problem. And again, for this backbone, for this architecture, two pre-training regimes are adopted, are employed. The first one is supervised pre-training using ImageNet and ImageNet 2021K, and also self-supervised pre-training using a subset of JFT, comprising just 70 million images. Another one is mobile former, which also combines convolutional neural networks with transformers. And in this case, the 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 research is about uh, an interaction between two backbones. One is the mobile backbone, this part on the left, and the other one is the transformer backbone. And what they are performing is cross attention between these two backbones to improve the performance of the foundation model. This is one of the latest work I have reviewed. This is about changing a mobile net or modernizing a mobile net with a vision transformer perspective. And in this case, they still use supervised pre-training on ImageNet, but they change the design of the mobile net to mimic the architecture of a vision transformer. For instance, here they modify the original mobile block to divide how tokens are mixed and how channels are mixed. This is within the mobile net. So basically, they change the block design of the original mobile net, and also they change how these blocks are pipelined within the whole architecture. So this is what I was talking in the previous works, is that there is a trend to combine convolutional neural networks with transformer architectures. And this is because for convolutional neural networks, there are a strong spatial inductive bias, and for transformers, there is a strong scaling. And there are three types of combining these two architectures. The first one is using a convolutional neural network at the beginning of the backbone, and then move to a transformer, or combine or interleave convolutional and attention blocks. And the last one is to have two branches or two backbones. One is convolutional and the other is full transformer based. This is very similar to mobile former, where there are two backbones for the architecture. So the question or the problem I'm trying to address in my research is how to design efficient networks to effectively encode both local processing and global interaction. And in this case, local processing corresponds to convolutional neural networks, and global interaction correspond to using transformer-based blocks. So this is what I'm proposing to accomplish this. This is a ResNet model within a ResNet architecture, but instead of using just convolutions, I'm combining convolution path with low rank path. In this low rank path, I'm generating global features from two components. One is the horizontal component, and the other is the vertical component. And the results are low rank global features, which are later fused with the features from the convolutional path to obtain better performance at the end of the backbone. And to test the functionality of this block, I proposed backward incorporation within the backbones, which means that this is, for instance, this is the original ResNet 18, and what I'm doing is replacing the last stage with the block I'm proposing, and just freezing the remaining stages from 1 to 3, just to verify that the block I'm proposing is actually working and it's not generating any instability during training. And during these experiments, I'm using ImageNet 1K with supervised training. In the second experiment, I'm replacing stage 4 and stage 3 and freezing stage 1 and stage 2 to check if the performance obtained during the first set of experiments, during this part of the experiments, is the accuracy is the same as using as replacing the blocks in stage 4 and stage 3. So these are two experimental sets that I'm proposing to verify the functionality of the block. And the reason for using backward incorporation is that training from scratch, for instance, if I want to train this backbone with all the stages, if I use the same block for all the stages, pre-training is going to take around 4 days. And also is when I employ backward incorporation, the testing of the block I'm proposing is inexpensive. It takes less time to verify its functionality. And also the first stages of the network act as the stem of the backbone. For instance, here stage 1 and stage 2 actually act as the stem of the whole network. And after performing these two experiments, I can analyze the training dynamics to spot if there is any instability during training, and also verify the accuracy during the training of the network. And if the accuracy does not outperform the baseline, or if the accuracy is not comparable with the baseline, then I just modify the low rank model. And The the interesting thing or the benefit of using this backward incorporation is that I can just modify the low rank model and verify its functionality in 2 or 3 hours. And also, I want to point out that the proposed model scales with feature size because I'm generating features with size of n times r, which r is the rank of the features. So if I increase the size of the features, the number of parameters is going to increase as well. That is different from just convolution, where the number of parameters scales only the with the number of channels of the convolution. So this is an analysis of the parameters count. And after analyzing layer by layer, I reached the conclusion that the parameter reduction, if I replace the block I'm proposing with the blocks or the stages at ResNet 18, the parameter reduction is almost 49%. And here, as I mentioned before, the parameter count of the block, the low rank block, scales with the feature size. In this expression, n represents the size of the features, and C in represent the number of channels. The input channels, C out is the number of output channels. So in this case, it depends on both. Depends on the number of input features, the number of output features, but also depends on the size or the size of the features. But the convolutional blocks only depends on the number of channels, the number of input features, and the number of output features. And these are the first results. The results I have obtained. The curve in orange is correspond to the model where I have replaced stages 3 and 4 with the block I'm proposing. The curve in blue correspond to stages 3 and 4, but without the low rank model. And the curve in green correspond to the integration of the block in stages 2, 3, and 4. And as we can see, if we don't use the model I'm proposing, the low rank model, the accuracy stagnates at 60% of top 1 accuracy. We can see here in this part of the figure. And if I include the low rank model, there is a boost of almost 6.5% of top 1 accuracy. And also, if I include the block model or the low rank model at stages 2, 3, and 4, the number of parameters is reduced, and also the accuracy is close to the best model. So that means that if I include the block at stage 2, stage 3, and stage 4, I'm also reducing the number of parameters, but the accuracy is still closer to the best model I have developed. So the results are the replacing the 4th stage of ResNet 18 with the proposed block yields a top 1 accuracy of 58 after 35 epochs. And if I replace the stages, the block at stages 3 and stage 4 the top accuracy goes up to 65 and 65.69% after 35 epochs. And just to mention, the best accuracy obtained with Resident 18 is close to 70%. So it is still below the best performing model regarding Resident 18. And also, if the low rank model is not included at stage 3 and 4, the accuracy goes to 16%, which is lower than when I replace when I include, sorry, the the low rank block at stages 3 and 4. And again, the torch implementation of Resident 18 reaches an accuracy close to 70%, but the accuracy of the proposed model is 3.16 lower, but I'm using around 40% less parameters than the original Resident 18. So the conclusions and next step, uh, a new ResNet-based basic feature extraction block is introduced in this work. It combines local features through convolutions and also global features through multi-layer perceptrons. The novel block addresses efficient local processing and also global interaction in vision models. And for the first experiments, I'm using ResNet 18 as the backbone for the initial experimental trials. And using this backward incorporation, I'm reducing the training time from 4 days to just 3 hours if I uh, retrain the model for just 10 epochs. And I'm using ImageNet 1K for the pre-training stage. And the next steps are that after validating the proposed block, I can include this block into another backbones like ResNet 15, MobileNet, or other hybrids between convolutional and transformer backbones. And also, after I have validated the functionality of this block, I can use I can pre-train the backbones with this block on sorry, I can use the pre-trained backbones on downstream tasks like semantic segmentation, post-estimation. And this is a summary of this work. This is the content of this summary will be included in the midterm exam, so you can take a look at it. And the methodologies that I have developed a novel ResNet-based block that fuses global features with local convolutional features to build a compact vision backbone. First, I integrate the proposed block into a ResNet 18 during the first experiments, then replace this block within the proposed model, pre-train the modified version of ResNet 18 on ImageNet 1K, and the next steps are to use the pre-trained backbone on downstream tasks like semantic segmentation and post-estimation. And the results are a compact yet effective vision backbone combining global features and local features. Okay, so this is the end of my presentation.
几分开始上课？现在呢？44吧。嗯。是大概是这样。那哦，那我直接开始继续讲这个第四章。那第四章是 Model Fitting and Optimization，就是模型的拟合还有优化。 那这个章节主要是在讲说，就是我们要怎么在一个含有很多杂讯的数据中建立这个数学模型，然后会做正规化处理。那大纲的部分有 scatter data interpolation 分散资料的内查 variational methods and regularization 夫的随机场。那我们先讲这个 radial basis function 镜像级函数。那这个真实的数据通常都是就是不规则的分散。那我们的目标就是要找一个连续函数 f of x， 然后要让这个函数可以穿过所有的点。以这个右边这个例图来看，就是我们可以假设这个 x 是已知的数据点，x 是这个数据点在这个三维空间的坐标。那这个 d 值它指的是这个 x 坐标对应到的实际值。那我们就可以把这个连续函数写成 f of x 等于 d。那常见的找这个连续函数的方法有两种，第一个就是 triangulation and interpolation， 三角的网格化还有内插法。那第二种是 pull-push algorithm。那我们先讲这个三角化网格内插法是怎么做的。那第一步骤就是 triangulation， 就是我们会用这个几何的方法来找到这个连续函数。那看这个下图这边，左边我们在一个三维空间有分散的资料点。那我们会先把这个三维空间中的资料先映射到二维的平面，然后我们会在平面这边想办法把所有的点连接成多个三角形。那要注意的是，我们在连接这一个点的时候呢，三角形就是必须 avoid producing long screw triangles， 就是要避免这个过于狭长的三角形，因为过于狭长的三角形可能会造成我们之后在计算内插的时候，这个计算误差被放大。那第二步骤就是要做这个内插的计算。可以看到这个右图这一边，我们以一个三角形为例，这个未知数是我们要求的未知点是这个中心这个蓝点的话，那我们的内插法考量到的就是这个三个顶点 value 1、value 2还有 value 3它们之间的权重关系。那如果我们的未知点是落在这个 value 1跟 value 3的这一条边的时候呢，我们的权重就只会考量到这两个顶点而已。那这一页是要再讲说，就是我们这个三角网格它内插法是使用 barycentric coordinates， 重心坐标法。那如果我们要套用在比较高阶的影像处理的话呢，可以用这个 cubic spline interpolations， 就是用三次方的内插法，我们可以得出一个更平滑的曲线，而且它可以涵盖所有的位置点。那这个范例就是讲说这个内插要怎么计算，这里是用向量的表示法，我们这个未知点 P， 我们是先取一个向量 AP， 然后等于 μAB 加上 VAC。那做一个简单的计算后，我们可以得到这一个未知点 Pxy 会等于阿法倍的 A 加上贝塔倍的 B 再加上伽马倍的 C。这个就是最下面这一行。然后这三个阿法、贝塔跟伽马就可以看成是这个顶点的权重，它们的 total sum 会等于1。那另外一种求内插法方法就是用 面积比例来计算。那同样，我们这个 alpha 可以看作是总面积分之这个 A 区块的面积。那再来是要讲第二种这个怎么取得连续函数的方法，是这个 pull-push algorithm， 就是推拉演算法。那我们看这个图例，这个最左边的是原始影像，那这个 B2 scatter data 是它含有很多杂讯，然后有很多的空洞。那我们这一个 B 图就是我们这个演算法的输入值。我们这个输入的影像会经过这个 pull-push algorithm。那这个演算法它主要有3个步骤。第一个是 pull， 就是我们会先把这一个大的scatter data image 先把它降低它的解析度，然后变成越来越小张。那在这个 pull 的过程中，这个影像它的就是空洞的地方会慢慢被补起来，只是因为随着这个影像越来越小张，它的解析度比较低，所以会相对比较模糊一点。那第二个步骤就是用 push 推的方法，我们把这个解析度最低的影像再把它推回来，就是从三角形的最顶端往下再推到最大张的高解析度影像。那第3个步骤就是 blend 合并，我们会去看说，原始影像中的那个 pixel， 它原本是不是已经有一个值了？那如果它有原始值的话，我们就会使用原始值；如果没有的话，我们就会使用这个演算法计算出来的数值。那这个 D 图就是我们的 pull-push algorithm 的结果，可以跟 A 图做比对。
我再讲一下，对。OK， 现在正在讲课的是那个第4章哈，是蔡华岭哈。那大家如果觉得他讲的好的话呢，到时候就请大家帮他那个投一票哈。那希望他能够拿到这个1万块哈，也就是这门课能够拿到那个100分哈，A 加哈。那另外的话呢the research part which is presented including the every chapter we will have 6 points on the research part, 2 points on the method and 2 points on the steps and 2 points on the results. So the research will be part of the examination. So I'm leaking the problem set anyway. Actually, because so every research will have 6 points. Okay, so 2 points on the methods and 2 points on the steps, and also 2 points on the result. Okay, and okay, I think that's all. 林希怀是哪一位？林希怀 ，OK， 好，你可以继续了。OK， 好。
那接下来要解释这个 radial basis function。那我们刚提到的是叫 mesh-based approach， 就是我们会建立这个网格来计算这一个连续函数。那这个 radial basis function 就是一种我们可以不用建立网格就可以得出这一个函数的方式。那直接讲这个数学式，这个 f(x) 它会被定义成一个 weight 权重乘以一个 phi 函数。那这个 phi 函数里面的 x 跟 xk 值分别是代表这个已知数据的位置，还有这个已知数据的位置是这个 xk。那 x 是我们的目标数的位置。然后我们计算的是它们2个之间的就是绝对距离。
这个是 norm，norm
哦，对 ，norm。
距离的话可以看不同的定义，你可以把 L1、L2、L3、L infinity 都可以，看你怎么定义。对，
那常见的这个 phi 函数的应用有这个高斯式，还有 Hardy multi-quadratic， 就是Hardy 的多维式，
而且是2次。
对，2次。 那这几个这个 phi 函数它都有2个参数，一个是 r 是 radial distance， 它代表的是这个就是2个点之间的绝对距离，一个是对辐射距离，一个是 scale parameter。那 C controls the size, radial fallout of the basis function, and hence its smoothness。那这一个 C 它用来控制是这个，我们可以决定说这一个phi 函数的影响力可以扩大到多少的范围，然后它也是决定这个我们的函式的平滑程度要怎么去设定。那这里有写说这个 x sub k be scattered data 的 equation 就是 needs to be satisfied like f of x。那这一个公式中，这个底 k 就是我们要求的实际值，就是我们会预想说套入这个 phi 函式的计算结果后，是不是可以真的符合我们要的这个实际数值。那在这个函式中，我们可以测量的是这个 x 值，那未知数就是这个权重 weight， 所以我们接下来就要讲说要怎么计算这个 weight 权重，也是一个 set of weights， 就是权重值。计算这个权重的方式主要有2种，一种是 minimizing the data constraint energy together with a weight。模型最小化的数据约束 data constraint， 然后我们也会考量到 weight penalty， 也就是权重的惩罚。那第2种是 kernel regression 和回归。那我们先讲这一个第一个方法，使用到的是就是 regularization。我们会把这一个radial basis function 用一个能量函式来表达。那我们的目标就是要找这个能量函式，它可以越小越好，就是代表我们可以花最小的能量来取得这一个连续函式。那这个 weight function 中，我们是写成e of 这个 weight set 会等于e sub d 加上 lambda e sub w。那这个 e sub d 它代表的是 data term， 就是数据的误差。其实也可以表示成就是我们要求这个数据的准确度。那 ew 是 weight penalty， 就是权重惩罚，它可以代表这个连续函式的平滑度。那这个能量函式中有一个参数浪达，这个浪达就是一个正规化参数，那它就是类似一个开关，我们可以用这个开关来决定说，我们希望这个能量函式中比较注重于这个 weight penalty， 还是比较注重这个 data penalty。
如果杂讯比较低的时候，那个浪达要大还是小？如果杂讯比较低的时候，
如果杂讯比较低的时候，这个浪达可以大一点。
不是不对的，浪达应该是要小一点点，因为你如果杂讯很多、杂讯很低的话，则你的 data 本身的 constraint 已经够强了，因为你没有什么杂讯嘛。可是呢，如果你杂讯很大的时候，那就要这个浪达就要怎么样？
小一点。
我们再讲一遍嘛，杂讯很低的时候，这个项就够强了嘛，所以呢，这个项呢就怎么样？
小一点。
可以小一点点，因为不重要嘛，因为杂讯很低嘛，资料量本身就已经限制就已经够好了嘛。如果说杂讯那个比较高的时候，对不对哈？那因为这个里面加了很多的杂讯嘛，所以呢，你要用这个东西让它有点比较平滑一点点，所以这杂讯比较高的时候，这个浪达要大还是小？
大一点。
要大一点，对。
嗯哼。 哦，那接下来是，那接下来简单的讲一下这个 ED 跟 EW 的公式。那 ED 它就是使用一个 phi 函式，就是我们刚介绍的 radial basis function，它要减掉 dk 值，然后我们会做这个 norm 处理，L2 norm 处理。那 EW 的话，我们会用这个肉次方的那种处理。当这个肉等于1的时候呢，我们叫它还有选择算子。那这个肉等于1的时候，这个就是称作 L1 norm。那当我们这个肉代入2的时候呢，它叫做pure least square problem ridge regression，就是称作 L2 norm。那因为我们要计算这个 weight set 就是会计算量非常大，所以我们另外一种解决方法就是我们直接把这个未知的 weight set 用我们的已知的测量值 dk 来取代。我们就把这个刚刚提到的 radial basis function 的位置改写成 dk。那虽然这样子计算量就会相对减少，可是我们在处理数值内差的时候，就是会造成就是某一个像素它的周围邻近域可能会因为内差法就是影响力叠加，然后造成误差被放大。那接下来要讲就是第二种计算位的方法，叫 kernel regression 和回归。那这种方法它是就是不用像刚刚一样解那种方程式，然后也不用算出这个未知的 weight set 值。那它的公式可以看到，它的分子就是直接套入我们刚刚提到的这个该写过的 function f(x)。那它的分母就是会再除以这个phi 函式，就是做一个正规化。那它的目的就是因为我们在做这个 f(x) 的计算的时候呢，要避免这个局部的那个加权平均它影响力，就是受到刚刚的计算，就是我们要确保它经过正规化处理，这个影响力才不会有偏差。那再来是要讲这个4.1.2章 overfitting and underfitting 过度哦，先放笑话。
对对对，笑话比较重要，谢题对。
哦，嗯嗯，好，等一下。PPT 那一页，这个要先结束。嗯，应该可以。嗯，PPT 那一页。可是 等我一下。等一下，谢谢。
我有算一个，因为我们西山要清点财产的话，会遇到这些，那你如果确认每一项财产的话，都可以找得出来，你可以参与去额外检查的时候，要确定每一样都可以交得出来。哦，OK，两位一样，每一样可以点。
是。
你搜寻一下这个哈，在 YouTube 上面呢哈，你搜寻那个我看一下，YouTube 上面的话要搜寻的是 AI written code is breaking Amazon systems， 来，AI written code is breaking Amazon's systems。Yeah, this one. Yeah, play this one. Yeah, play.
好，那我们继续讲这个 overfitting and underfitting，就是过度拟合还有拟合不足。那 overfitting 代表就是这个模型它太复杂，然后把很多杂讯都学进去，所以这个模型它训练出来结果可以看到这个红线这边，就是它会有 spurious wiggles， 非常严重的摆荡。spurious。
Yeah, spurious。
那这张图就是举出来这个 好，那继续讲这个 plausible，它代表的是说那个模型的训练数据完全符合我们的实际分布。那接下来要讲是用这个数学函式来表示你拟合的状态。那我们用这个前面提到的 energy function 来表示。那这张图就在讲说，这一个浪的参数，它是从左到右是越来越小。那它就是显示说，当这个我们的 function 在 validation，也就是验证还有 training 的 error 很高的时候呢，我们的这一个浪的参数就应该要带入比较大的值。那这个过程就是可能造成 underfitting。那当这个浪的参数值带于比较小的话呢，就有可能造成 overfitting，也就是当我们的 training error 虽然显著的下降了，可是我们的 validation error 反而是往上升的。那接下来是要讲这个 data set 怎么 split。我们这个常见的资料集会分成 training set 还有 validation set。那我们这边提到的方法是用 k-fold， 就是我们会把这个 validation set 分成 k 等份，那每一等份它可以当成，就是每一等份可以当成一个 validation set， 然后会进行 k 减1次的训练 ，total 总共会跑 k 次训练。那接下来是要讲这个 robust data fitting， 就是稳健的数据、强健的数据拟合。
资料拟合。
对，资料拟合。那它就是指说，我们的数据里如果有很多离群值 outlier 之类的，还是可以让这一个函数完整的呈现出真正的趋势。
这个data 我还是喜欢用那个资料，我不喜欢大陆的那个数据，我们
资料。
资料，
那这个 robust data fitting 同样是用这个 energy function 来表示。那可以直接看到这个 energy function， 它多了两个参数，一个是 ER，那这个 ER 它代表的是 data penalty， 那 RK 代表的是 residual error， 就是残差。那这个残差值是指说我们的模型预测值还有真实之间的差异。那这个 ER 它是用这个 RK 取 norm， 然后再用肉函式做处理。最后这一行的公式在讲说，原本这一个能量函式是用 ED 代表 data penalty， 那我们在 robust data fitting 中，我们会把这个 ED 用 ER 来兑换，那它同样是这个 data penalty 的处理。那接下来这一张图就是，我们这个 penalty function 中的肉函式，它含有 alpha 跟 c 两个参数。那这个参数的调节就会影响到我们这个 loss function 的效能。 这个参数中的 c 它代表是 scale parameter， 就是我们误差的我们定义多少算是一个误差。那 alpha 是 shape parameter， 它指的就是误差多大的时候呢要被忽略这样。那右边这张图就是我们把这个肉函式做偏微分的处理。那可以看到，当我们这个我们直接看这个橙色的曲线，它的阿法值设为负无限大，也就是回刚这页这个定义讲的，当这个阿法值如果设为负无限大的话，就是要被忽略。我们是给它一个 range 是负无限大。那在这个偏微分的处理的时候，当这个误差值是正负6c 的时候，就是比较大的时候呢，我们的 penalty 会设定会呈现0。那曲线是这样子。那接下来要讲的是 variational methods and regularization 变分法还有正规化。那会再提到 discrete energy minimization， 就是离散能量的最小化，还有 total variation 全变分， bilateral solver 双边求解器，还有 application interactive colorization 就是互动式着色。那我们刚提到的方法cannot directly quantify and hence optimize the amount of smoothness， 就是没办法得到这个函式最佳平滑度。然后 no local control over where the solution should be discontinuous， 也没办法控制说这个区域哪些部分可以有这个不连续面。那我们这个变分法，它一样会定义一个能量函数来表示。那这个能量函数，我们先看在一维空间的能量函数，它会用 epsilon1， 也就是一阶的导数，还有 epsilon2 二阶导数来表示。那这个能量函数是用来处理这个函式的平滑度。那同样这一个全变分可以套用在二维的空间。那二维空间上，它这个 epsilon1 是处理曲面的斜率 ，epsilon2 是处理这个曲面的弯曲程度。那再回来看这个一维空间，它的 epsilon1 就是代表这个函数的斜率变化。那 epsilon2 是代表它的弯曲程度的。那刚有提到，虽然我们用这个 epsilon function 来处理这个平滑度以及平面的断点，可是没办法完全呈现这个影像该有的原始样貌，所以我们会引入另外一种方法，叫做 epsilon cc controlled continuity， 就是受控的连续性。那这一个函式中，它含有2个 function， 一个是肉 function controls the continuity of the surface， 就是它用来控制这个表面的连续性；一个是 tau controls how flat the surface wants to be， 它用来控制这个平面的平坦程度。
好，我们今天就到这里。OK。
好，那今天先到这里，就先下课了。